Okay, so good morning. This is really our first lecture for the course. Last one was more to set the tone and the background, give the background for the course. So today's today's goal is to understand first one is to understand what is the meaning of the words covariance and invariance. So one second. So the typical usage of this thing, for instance, of say an example of that is okay. So I will give you an example. Maxwell's equations are manifestly covariant under rotation. So what is the meaning of this statement is what I would like to get to. Okay, if you know it, very good, congratulations. And second sort of thing is to introduce you. So introduce the groups O3 and SO. So this is our goal, okay, for today's lecture. Just these two simple things. Okay, so this is what is the plan, and so let's get going. And so
there is so much echo from your side.
is it okay now?
Yes, sir, fine.
That was my fan. So now I'm sunk. I'm in warm Chennai. So I'll try a different fan. Just give me a second, okay?
We can manage, sir. You put it on.
Yeah, thank you for pointing that out. Is it okay now?
Yes, sir.
Yes, sir.
Okay, fantastic. Huh? Okay, so I switched to a table fan, which makes less noise. I know that much. Okay, so we will start with this kind of experiment. We'll start with this kind of a thought experiment or an imaginary experiment. Not really a thought experiment because there's nothing deep out there. Okay, so two students, A and B, decide to verify Newton's second law, okay, which states the following: M okay, so in components, okay, and I will, instead of this, I will write, this is nothing but acceleration, so I will write this as M A1 equal to F1, M A2 equal to F2, and M A3 equal to F3. Okay, so we are going to use, instead of calling it X, Y, and Z, I will use 1, 2, and 3. Okay, so the advantage of this is that we can, we can go to 2 dimensions, 3, and we can make, we could write a fourth equation, MA4 equal to F4 and so forth. Okay, so this is what they want to verify, and then, so their idea, A measures acceleration and B measures force. Okay, so they'll get they'll get a triplet of numbers. So they get A1, A2, A3. This is from A, 3 numbers, and F1, F2, F3, and B. Okay, so the idea is that you go ahead and you do this F1 upon A1, F2 upon, this should be, this is a question mark, right? Right, so this is what they want to check. Okay, so they go ahead and they've got these numbers. So what happened in reality? Okay, they found 3 different distinct ratios. That cannot be explained even with error bar. So now comes the question to you. What went wrong? So now the floor is open for answers. What could have gone wrong?
We have not specified the frame of reference, whether it was inertial or not.
Okay, no, they're doing it in a lab, regular lab. They have some particle which is moving, so they are both in the same frame.
Okay.
So both of them, I mean, in that sense, it's okay. But I mean, you are thinking in the right way. So I don't want to say you are wrong. Yeah.
So there could be some unbalanced force.
No. So the forces were measured properly. The acceleration also was measured properly with some non-experimental errors, but both were measured properly. So it's not an error in measurement. That's what I meant by saying, cannot be explained even after for accounting for experimental errors. Okay. So we have to play Sherlock Holmes. Yeah.
They are in different reference frames.
Yeah, in what sense? Yes. Okay, good.
Sir, they are accelerating with respect to each other.
No, nothing. They are in the same room. If they're acceleration, one guy is running away from the room or something. We are in the same room.
Same coordinate systems.
Okay, good. Okay, so the thing is that they did not. I mean, I don't know how you guys were in the lab. Most of us would go to the lab and we want to do this experiment, so we'll do the experiment. But who knows? Olympics is going on and we want to watch some our favorite event or whatever. India playing Belgium or something like that, and I want to see that, so I want to finish my experiment. And so they just quickly measure it and do the analysis later. So they did not agree on the coordinate system. So this is what happened. So really, so in some sense, so this answer, okay. So let us do this. Let x1, x2, x3 denote the coordinate system A and okay, so we'll do that. And for simplicity, we can even ignore this. Let us assume at least that A they don't agree on the origin, agree on the axis, but on the origin. Okay, so x1, x2, x3, all of them being 0 is the same as x prime, x2 prime, x3 prime being equal to 0. Okay, so now we need to know. So once we have this thing, so we need to correct. So the question now is, how do we implement the correction so that we can verify? Okay, so let's now
Both mean same coordinate system is Cartesian coordinate system.
yeah, they are Cartesian, yes. Yeah, let's assume they are Cartesian. This is Cartesian. This is measured by A, but what is measured by B is F1 prime, F2 prime, F3 prime. This is correct. So now I've accounted for this fact.
Excuse me, sir.
Yeah.
So, what you meant to say was that means they have both measured the experiment in the Cartesian coordinate system, but they didn't agree on the coordinate axes. Means
Exactly. That's what I
the
was saying.
axes for the both will be different, but both
Exactly.
have done in the Cartesian coordinate only.
Yeah, absolutely. Okay. Right. So now really what we need to do is we have two ways to do. Either we find out what how this will so two options. One is convert acceleration into B's coordinate system. Or second one is convert force to A's coordinate system. Right? So now we need to ask how, so it just reduces to asking the statement as to how both systems are related to each other. Okay? So we need to work out. So let's so let us do that. So I'll form a three column vector with x1 x prime. So this should be equal to some matrix. Okay, so let's just call that matrix and write some matrix. So I can't use A because A is for acceleration. So let's. Okay. If, plus we could have had some constants, C1, C2, C3, but we said that the origin, so this is 0. Okay, by our choice because both of them agree. So this is the most general change that could happen. Okay, but so let's just call this matrix with entries with little b. I'll use capital B. So I'll just use short form for this. Okay, where I and j run from 1, 2, and 3. So when it's obvious, I won't say that. Okay, so that's what you get. So we can rewrite this equation as follows: x, I'll put a vector here, prime is equal to b times the short form for the same thing. Okay, so what are the properties of B? But we need to know what is this B, right? Do you agree that this is what should happen?
Yes, sir.
Yes, sir.
Okay, so
Yes,
what
yes.
are the properties of B? Okay, so once we, okay, so this is a question to you. So what do you think should be the properties of B?
It should be invertible at least.
Very good, important. Any other property?
Dimensions should be same as the vector.
Yeah. So B is dimensionless. So all the numbers B11, B12, etc. are all dimensionless. Correct. Okay. That I'm not writing, but that's obvious. Huh? Orthogonality. What is that? Okay. So we need that, and so that's correct. So somebody used the word orthogonality. That means what?
The product of the matrix with its transpose will be 1.
Well, yeah, that's absolutely correct. But the question is, where does that come from? Okay, so question is, where does this come from?
So the length of the vector remains same.
Okay, very good. Where does this come from? So partial answer is the length of a vector in both. We'll use the word frames now, okay? I'll use the word frames. That means A is coordinate system and B is coordinate system. Okay, but this is not enough. Okay, so the additional property is that both A and B choose coordinate axes that are orthogonal to each other. Okay, so let's say that A chooses E1 hat, E2 hat, and E3 hat. And the key point here is this is a right-handed triad, right? So this is a right-handed triad. What does that mean? It means first thing is that, so let's write something. EI dot EJ is what? It's equal to
The delta
Ij, which is called the Kronecker delta. Okay, so delta Ij is nothing but is equal to 1 when I equal to j and 0 when I not equal to j. Okay, so this is okay. So this is orthonormality actually. orthogonal means E1 dot E2 is 0. They are perpendicular to each other. Normalized means E1 square is 1, which is this. Okay. And right-handed means E3 hat is equal to E1 hat cross E2. Okay. So similar. Okay. So both have chosen these things. So we need to know. So the problem can be switched to saying we need to know. So now we can, the same question, here I wrote it in the form of, where was this? Yeah, in terms of this, but really I could have actually written it as how is, say E1 can be expressed, say, in terms of E2 prime. So this is just, so E1 will be some, so the point is that any vector can be expanded in terms of these guys. So in particular, E1 hat is some vector. Okay, so let's just do this, and then this should be writable as, I'll write some vector. I'll write some matrix again. D11, E1 prime plus D12, E2 prime. I'm not using B. It will be related to B.
Sir, one
Yeah.
question.
Yes, go ahead.
So this discussion about orthonormality and right-handedness, why does that imply that we need orthogonal this matrix B?
No, that is the general. That is the general statement, no?
Sir, I understand why B must be invertible, because if we take it to B must be able to take it to that side.
Yeah.
But why orthogonal? And that is
That's what I'm getting at. So usually when we write things, we choose basis, Cartesian basis or whatever, or any, even you could have even weird basis, but doesn't matter. Usually you choose the basis vector. So this properties you normally have, no? This property which I have. This is what I'm using. Right. So, I mean, you could work with non-orthogonal coordinate systems, but those are, I mean, so then a delta ij will get replaced by some symmetric matrix. You can work with that. Okay, but this is the simplest.
Sir, but why does this require the B matrix itself to be?
No, we haven't proven that. We haven't proven that. We have to show that. That's what we have to show. Some people seem to know that, so I don't know, you don't know, so we are going to figure it out. Okay? Yeah, absolutely. I haven't shown that. Okay, so here I'm just saying that E1 is just is some vector in from the viewpoint of B, and I can do this. Similarly, E2 is D21. Right? Do you agree with this? Okay, so this is what we have. So again, I can do this. I can rewrite this. But now what I will do is I'll write this not as a column vector, but I will write this as a row vector. For reasons which will become clearer later, or even if it doesn't, it doesn't matter. Okay. I have to put a transpose here because of the way I wrote it. If I want to, or I should have called this D21, but I didn't call it. So okay, is this clear? This transpose is clear. I need to put that because it has to act properly. Okay, so this is a short form way of writing it. And D is this matrix. Okay, so now comes the claim, which is easy to verify. Okay, so what we have is EI hat dot EJ hat. Okay, you have to work this out. Equal to delta IJ implies that delta IJ. So we can go ahead and take this and you can rewrite this in terms of primes. Okay, and of course, both are true. What we get that implies that this matrix D okay. So it just says that, so far we just wrote arbitrary matrix thing, but now we have to use, for instance, let's do one of those, let's do two of those things. So let's say that what we have is E1 dot E1 hat should be equal to 1. So let's just go ahead and do that. And if we do that, we'll see something very simple. We will see that this implies
Hello, sir.
yes.
So here we are assuming that one of like we have taken EI and EJ and EI dash and EJ dash.
Yeah.
So we have assumed that one will be true and we are going to prove the other one.
No,
like
no. We are assuming both are true, and that will give us a property of D.
Okay.
Okay, because each person, so this is chosen by B, this is chosen by A, both of them will choose orthonormal basis.
Okay, sir. Thank you.
Okay, so it imposes condition on this matrix D, and what is that condition? I'm saying that is this condition. So you can write it out and check what I've written. So let's do one more. E1 dot E2 dot should be 0. So this implies that D11, D21 plus D12, D22 plus D13, D23 should be 0, so on and so forth. There will be more conditions. We need to check that these can be written in this form. It's either D transpose equal to identity or, okay. So, and there are more expressions. So this is what you can check. Okay. So this is what we get. So now let's make a definition. Okay. So check. So this is what you need to check, that all this combines to give you a very simple formula. Okay. So definition. A matrix E is said to be orthogonal if this definition. Okay. So now so short form. So we just says that the condition here is D is orthogonal. But before that, we need to go back to our original problem. How is B related? So for that, I need a little bit of work. So let us look at the acceleration.
Sir, I think the B matrix also should be symmetric.
No, B need not be symmetric. D is also orthogonal. We'll see. B is either equal to D or D transpose. We'll see
So
that in a
if it
moment.
is not symmetric, then how can we write that D dot D? I mean, the inner product of the matrix is uh, D11 square, D11 square plus D12 square plus D12 square. How
Yeah.
can we write it as the inner product with it?
I can give you plenty of examples of matrices which are not symmetric and still are, they satisfy orthogonality. I mean, I don't know. I don't see that condition is not obvious to me.
Okay, sir.
Okay, so for this I need to do a little bit of work. So the acceleration for vector, I can do it this way. So usually, so the correct way to write, would have written it is like this, right? A1 E1 cap plus A2 E2 cap plus A3 E3 cap. Okay, but we can write this in a fashion which you will like in a moment, and you will understand why I put it as a row vector. Okay, so this is what we have. We can write similar thing for force, right? You can see this is just standard multiplication of row with a column. You get back the previous thing. But now we know that E1, E2, E3, okay, is related to D. How was it related? Like this, right? So I can rewrite this as equal to dot D transpose dot. Okay?
Okay. First expression of E, you have written E2 prime. It should be E2, I think. E2 prime, E3 prime.
Oh, I make lots of mistakes. Now is it okay? Thank you. Thank you. Any more mistakes? Okay, good. Okay, so now we see that so morally this thing should be, what should this be equal to? This combination D transpose acting on
Primed acceleration.
Yeah. Okay, so we get this formula which says that okay, so, and you can do the same thing similarly. F1 prime, F2 prime, F3 prime. There's nothing special about acceleration. I can repeat it, I get these things. So now we can go back here to our definition of B, okay, the matrix B. So B took you from prime to 1, right? That's what you get. Bx. So let me write that. Okay. So now what is the relationship between B and D? What should B be in terms of D?
D basically transpose.
Yes. Okay. So, I mean, a priori it looked like B should be unrelated to D, but it is, because all these guys have the same property. The same arguments go through. So, So we only used, so far what is it we have used? We have only used the property that it is orthonormal matrices. So we got that D should be a orthogonal matrix. Okay. So B is completely determined. So they're not independent of each other, and it's thus orthogonal. Okay. So your exercise is to check if D is orthogonal, D transpose is also orthogonal. Okay. So exercise. Show that if D is orthogonal, so it's actually very trivial. So we still have to use exercise. Okay, so what is it? Show that you need to do this, right? E2 cross, this is what we want. Right, so this is the statement that all E1 cross E2 is along E3. Okay, it's a unit vector, etc. But okay, but this is what we show that this implies okay. So definition: an orthogonal matrix P is said to be special if state is this clear? Okay, so this exercise you have to do, but it's a very nice exercise. And there's a formula that I hate with all my heart, which is to express the cross product as some determinant of something. And but that's probably the shortest way to get this answer. But okay. So this is also, we have two definitions, and so this so there are some properties of orthogonal matrices. Okay, the identity matrix. Okay, so if D is orthogonal, then so is D inverse. In fact, that's equal to D transpose. Okay. Third property, which is very important, if D1, D2 are orthogonal, so are the products What I'm saying is, if D1 and D2 are orthogonal, D1 dot D2 you multiply them, or D2 dot D1, whichever, both of them are also orthogonal. Okay, so last one, which I will prove. Okay, this proof I will give. Or if somebody knows how to prove it, tell me. So what is an orthogonal matrix? So take determinant on both sides. What is the determinant of identity matrix?
1.
So
1.
Okay. But left hand side is the product of two matrices. So this is equal to okay. What can we say? Is there a relationship between the determinant of a matrix and the determinant of the transpose of the matrix?
So 1
they are
by
equal.
determinant of.
They're equal. They're equal.
Both are same, yes, sir.
Not 1 by. It's not D inverse.
Yes, sir.
So
Okay.
D
It's just transpose.
the
Okay. So
transpose
this.
of D equals to D, right? D inverse, right?
No.
Which is that.
No,
No.
both are same.
Yeah, that is true for. That is true only. I mean, that is true for orthogonal matrices. We are asking for a generic matrix itself. It is true.
Okay.
Yeah. What you're saying is true. So that says that determinant of D whole square is 1. So this implies determinant of D can be either plus or minus 1. Okay. And we have already defined, see, plus 1 is special. Okay, so exercise is verify properties 1, 2, 3 above. Okay, this is one. Second one is verify that special orthogonal matrices Okay, so let's look at what were the properties. So it just says identity matrix is special orthogonal. So we need to only check it's orthogonal already. Special means you need to check its determinant is plus 1. Done. If D is orthogonal, so now we have to read this as if D is special orthogonal, so is D transpose. Again, that happens because D inverse. Okay, so determinant of D inverse is same as determinant of D transpose, which is the same as determinant of D, which is plus 1 if it is special orthogonal.
Sir, are we allowed to take determinants on both sides?
Otherwise, there is no meaning. Yes, of course.
But what allows it? Like what exactly is the operation?
If you if A equal to B, okay. So the question, so in our case, A is a 3 by 3 matrix, B is a 3 by 3 matrix. When are two matrices equal?
When each of the elements are equal.
End of story. So any complicated function of those things, such as determinant, it's not just determinant, any function that you want to take, which is a function of all the entries, it should be equal, right? Because it's a way, I mean, A equal to B is a very strong condition. Every term will have to be equal to the other. So arbitrary functions of those 9 variables should also be equal. So yes, I'm allowed to use determinant. Determinant is a very specific cubic function of those variables.
Okay, sir.
Yeah, determinant is well defined, absolutely. Okay, is that clear? Okay, so yes, determinant is only a special case. So this is what we get. Okay, so these properties 1, 2, and 3, okay, define something called a group. Okay, so this is a well-defined object. We will look at what a group is. We'll do the formal definition later, but what I'm saying is that it's not like I cooked up properties 1, 2, and 3. Okay, they are something which is well known in mathematical literature, and they are with one more additional condition on associativity, which is kind of true for all matrices. But there's a fourth condition which we are not looking at. But so what we get is a group. Okay, so so some notation now. Okay, we have been implicitly saying that with real entries. Is this right now? I'm just calling it a set. It's just a collection of all matrices, but they all satisfy these properties 1, 2, and 3. That you take any first thing is identity belongs to the set. Each of these sets. Okay, if you take any two elements in the set and multiply them, you get a third, another element of the set. It's closure. It's called. Okay, so these are the names, and you can see I've used n here. And what we were interested in is the case of n equal to 3, because we assumed that the matrices were 3 by 3. But if you look carefully, nowhere in our considerations that 3 was special. There was nothing special about 3. So we could do these things. Okay. So now, so our interest at the moment, at least, okay. So let us look at we'll write something like this. SO3 matrices okay, and the reasoning is like this. So let me draw some picture here. Okay. So what this says is that, so you think of these E1, E2, E3 as made up of some rigid wires of length 1, which form which are put together, and the prime coordinate system also to be something like that. What this says, the reason I call it a rotation is that there exists a rotation, so origin is preserved, so there is some way I can rotate such that, E1 can be mapped to E2, E2 prime can get to map to this, and E3 gets mapped to E3. So that's why these are called rotation matrices. And you can check that exists such a matrix, and that will be a role. So that will be we have shown that it has to be a special orthogonal matrix. So, but physically it corresponds to rotating the axis. Okay, so they'll be called rotation matrices. But what about? So that covers rotation matrices. So, but what about orthogonal matrices? Okay. So let E be the following matrix. Okay, and P tilde be the matrix minus 1, 1, 1. Okay, you can check that P and P tilde are orthogonal but not special. Very, very easy. So not special is easy to see because you take determinant of P, it is minus 1. Determinant of P tilde is minus 1. Okay. So usually P is called parity. It is called the parity matrix. Okay. I will end today's lecture with the following claim that any orthogonal matrix B with determinant of B equal to minus 1 can be written as oh, something went wrong, I don't know. Okay, so I think my this thing discharged. So anyway, I just wanted to finish. So I just will state in words what happened. So what I said, if D is an orthogonal matrix with determinant equal to minus 1, you can write it as P times some rotation matrix. How do you see that? So you look at the matrix P and you look at P square. What is P square? Look at your notes and tell me what is P square. Identity. Okay. So it is a special orthogonal matrix. Okay. So but P. So what you can do is if you give me a matrix D, I just multiply it from the left by P. That becomes, then you can check that it becomes a special orthogonal matrix because determinant of P is minus 1, determinant of D is minus 1. So that is your rotation matrix. End of story. Proof. So that's it. So the whole point here is that there are two types of, so you can see that if you look at the set of rotation matrices and you just multiply them by P or even P tilde will work. P tilde square is also 1. So either you multiply by P or P tilde and you get back the original matrix. Okay. So this is the setup. And so next time we will see how these properties are important. And we will define what is a vector, and we will understand the ideas of covariance, invariance, etc. of equations. Okay, so I'll end with only completing one half of what I set out to do, but that's okay. So any questions before we wind up for today?
So can you tell some references for this, for reading more about this?
There's no need to read more. If you can reproduce all my claims, I'll be very happy.
Okay, sir.
Okay. I mean, this is not like some high funda stuff. Okay, it's just something where you look at the definition and do these things. As we go further, we will need more things, but this is not one of those where you need to look for references. It becomes a wild goose chase, and the level might become too high. I mean, you can become very, very fancy. So, no reference for this.
Sir, can you access the note of today's lecture?
What?
The note of today's lecture, can you access that?
Yeah, it will come on Moodle. So one more thing is that every lecture will be posted on Moodle, the PDF file, and the video will be posted on Google Classroom. So which reminds me that I should stop recording right now.